So here we're looking at halogenation from the perspective of synthesis, hopscotching from the reactant straight to the product, just keeping a couple details in mind that we know from the mechanism. So for example here, it's anti-addition. So the two bromines or the two halogens that we add will add in facing in opposite directions, either coming out or going away from us. So you'd see the alkene. You'd say the big category of reaction that this can do is addition. In addition reactions, you almost always just have the carbon skeleton, the sigma bonds, and the pi bond goes away. You use those electrons from this pi bond, you use that as extra molecular glue to stick something new on the molecule. Okay. Well, what do you stick on? You look at the recipe. We have Br2, just a halogen. So this is going to be halogenation. So we're going to add one bromine on each of these carbons in the double bond, and we have to make sure that we add them anti. So if we have one bromine on one coming out at us, the bromine on the other will have to be going away. Now, we need to make sure that these atoms that we added the bromines on are truly tetrahedral, so they need two bonds in the plane, one coming out and the other going away. So here, I need to make that methyl group a dashed wedge. And here, two bonds in the plane, one going away, and the other has to be coming out. So I need to change that methyl group to be coming out at us. Now notice that these two atoms are chiral centers, both of these carbons. And so you will, in addition to that, you will want the enantiomer, because the molecule that we start off with, the alkene, is flat. Each of the sp2 hybridized carbons in the double bond are trigonal planar. So they are flat, and the double bond in general is flat. So there's no preference for how this will attack one direction or the other. It'll be equal, and so you'll have an equal 50-50 racemic mixture of the two enantiomers. Now when you want to get the enantiomers, you switch the configuration of the bonds. So if on the left the bromine is coming out and the methyl group is going away on top, on the right the bromine will be going away and the methyl group coming out on top. If on the left the bromine is going away and the methyl group is coming out on the bottom, on the right the bromine will be coming out and the methyl group will be going away on the bottom. And so the chiral centers here will have switched, both of them, as you go from the left molecule to the right. And so since all the chiral centers switch, they are enantiomers. And again, you get that as a 50-50 racemic mixture. So B, you see an alkene, you think addition reactions, as opposed to substitution or elimination. You look at the recipe, you see that you only have a halogen, and so you're going to be doing halogenation. So redraw the carbon skeleton, but without the pi bond. The two carbons that were in the double bond, those are the carbons where you're going to add the bromine. Now they're going to add anti. So if you have one of the bromines coming out at you, the other bromine will be going away. Now, we need to make sure that these are tetrahedral. For this molecule, the atom on the right, we have two bonds in the plane, one going away. That means the other methyl group has to be coming out at us. So we modify that so that that's coming out at us. So that's one possibility, but because the alkene is flat, because the double bond is flat, the carbons in it are trigonal planar, the bromines are going to add from both directions. They could do this molecule from both directions. They can make it. And so we will have a racemic 50-50 mixture of the two enantiomers. To get the enantiomers, you just switch all of the stereochemical bonds. So if one is coming out, you make it going away. If one is coming out, you make it going away. If one is going away, you make it coming out. And so these two molecules are the two enantiomers that you'd get in a 50-50 mixture if you did bromination with this alkene? Okay, C. You see an alkene and you think addition reaction as opposed to substitution or elimination. What are you adding? Look at the recipe. We only have a halogen, so we're doing halogenation. Halogenation, redraw the carbon skeleton exactly as it is, just without the pi bond. And then we're going to add 2 bromines, one on each of the carbons in the double bond in the reagent. So this carbon here and the carbon there, that's where we're going to put our bromines. Now, if one of the bromines is coming out at us, the other bromine has to be going away. These are anti to each other. Because we have a chiral center here, we have to draw the enantiomer. So we'll have that same molecule. The enantiomer will be the same molecule, but we have to switch the configuration of any of the stereochemical bonds. So if one of the bonds are coming out at us, we have to switch it so it's going away. If another bond is going away, we have to switch it so it's coming out at us. Now technically, this bond on the right doesn't matter because the carbon that's attached to is not a chiral center. So whether the bromine is going away or coming out at you is the same thing because that carbon that it's attached to is not chiral. But I'm including it here, I'm including the stereochemistry here just to emphasize the point that the bromines add anti to each other. And so you would get a 50-50 mixture of these 2 enantiomers if you did bromination with this alkene. Okay. D. We see an alkene, and so you would think addition as opposed to substitution or elimination. What are you adding? You look at the recipe and you see bromine, just molecular bromine. And so all we have is a halogen, so we're going to do halogenation. Redraw the reagent exactly as it is, just without the pi bond. The 2 atoms that were in the pi bond, those 2 carbons, that's where we're going to be adding the bromine. So we'll have one bromine pointing in one direction, let's say coming out at us, and the other bromine will have to be pointing in the opposite direction because they add anti to each other. Because the bromide ion has to attack on the opposite side of the double bond as the bromonium ion because the bromines are so big and bulky, as we explained in the previous video. So that's one of your products. That is actually each of the places where the bromines added are chiral centers, and so we just have to switch the configuration of all of the bonds. So the bond on top that was a solid wedge becomes a dashed wedge. The bond on the bottom that was a dashed wedge becomes a solid wedge. When all the chiral centers switch like this, you have an enantiomer, and so these are the 2 enantiomers that you'd have in a 50-50 racemic, right? Racemic mixture when you do bromination with this cycloheptene. So hopefully that gives you a sense of how to think about bromination from the perspective of synthesis.